Okay, this question, I will say the first part is actually very easy. The first part only require you to apply the concept of stationary point, which is dy dx equal to 0. So in this case, right, it's actually not very difficult because you are just given a cubic function. And then when you differentiate, you get a quadratic. Okay, so the quadratic will give you two stationary points. And anyway, they don't even want the full coordinate. So they are just asking for the x coordinate. So the first part is kind of giveaway. So you shouldn't be making careless mistake in the first part. The problematic part is actually the second one. You need to apply the maximum minimal idea. So usually the maximum minimal idea happen for area and volume. Like you prove volume and then you find minimum volume or maximum volume, okay, or area. So this time around, we wanted a maximum gradient. So a lot of people will get my block, okay, and I will say this concept hasn't appeared for quite a while. So gradient is maximum. So I'm actually showing you two methods. Okay, so first of all, you must realize that when we say gradient maximum, gradient is actually represented by dy dx. So the dy dx is actually always known as the gradient function. So we want the gradient to be maximum means we want dy dx to be maximum. So we want our dy dx to be maximum. It's like you want area to be maximum, but this time around, you want your dy dx to be maximum. So the first method is actually to observe that your dy dx is a quadratic function. Your dy dx is a quadratic function. And because it is a quadratic function, it allows you to complete square. So if let's say your dy dx is not a quadratic function, this complete square method doesn't work. Okay? So in this situation, your dy dx is a quadratic function, so I can do the complete square. So I'm not going to go through the steps of complete square. I assume you should be okay with the complete square. There shouldn't be any careless mistake. So the whole idea is where you do the complete square, you should get the maximum or the minimum. So the underlying concept of complete square is always to get the maximum or minimum value. So previously, you usually complete square for y. So when you complete square for y, this is the maximum value for y, or it can be the minimum value for y, because the complete square is for y. So in this case, you are completing square for dy dx. So the value here will be the maximum or the minimum. In this case, it's a maximum function. So this is the maximum gradient. Whatever you complete square for, you get the maximum value for that item. If you complete square for area, you are getting the maximum area or you're getting the minimum area. If you complete square for volume, you are getting the maximum or minimum for the volume. In this case, you complete square for dy dx. You complete square for gradient. So the maximum value is applicable to gradient because your complete square is meant for gradient. And you can also find the corresponding x coordinate. So the corresponding x coordinate usually is done by setting, you can imagine you set this to 0, and that's how you get the x equal to -1/12. Okay, so okay, the whole point of this question is after you apply the concept of maximum gradient, you can get the coordinate of P, and you need to justify that P is also the midpoint of AB. So the midpoint of AB, you got to come back to this. So this one is like the A and this one is B. So you don't have the Y coordinate. So obviously you actually need to go and find the Y coordinate. So you get a proper coordinate. Okay. So, okay. Actually, if you don't find the y coordinate, it is still okay, because after you get the x coordinate for P, you use the midpoint from your previous x coordinate, you will find that you actually get the same. So the whole thing is you apply your concept of maximum gradient, get the coordinate of P, and you need to show that it's actually the midpoint of AB. So the midpoint of AB is used from the first part. Okay, so you can prove it by the x coordinate, then that's fine. Okay, so like I mentioned, right, I'm using the complete square method because the dy dx happen to be a quadratic function. In the case where dy dx is not a quadratic function, this complete square is not workable at all. Okay, so in the case where it's not workable, the alternative is this, which I can also use it here. So this alternative method, right, can be used for any gradient function, whereas the complete square method can only be used for the quadratic function dy dx. So I'm going to like label G as a gradient. So I'm going to label G as a gradient, and like we mentioned just now, gradient is measured by dy dx. So this is the gradient function. So G stands for gradient. It's like area stands for something. So when I want maximum gradient, I will differentiate gradient to be 0. So it's like I want maximum area, I will differentiate area to be 0. If I want maximum volume, it can be maximum or minimum lah. Okay, I'm going to do a dv d something equal to 0. Okay, so I just literally take it as, oh, this is gradient. Okay, then I'm just going to differentiate and then apply the dg dx equal to 0. No need to go and think about second derivative and confuse yourself. No need. Some of you in your head, then you'll be thinking, why am I doing a second derivative? Don't think about it. You take it as an item. A gradient is an item, like area is an item, like volume is an item. So just go with it. So gradient is like an item in area. So if you go with it, right, you also get the x coordinate. And if you put the x coordinate into the gradient formula, you also get the maximum gradient. And of course, you can also justify that it is actually the midpoint of AB. Okay, so I repeat, there are two methods. So the second method is a method that can be applied to all different dy dx function. However, the complete square method can only be applied when your dy dx is a quadratic function. Okay, so you must know the limitation. Okay, you must judge it for yourself, but the underlying concept is very important. Okay, don't overthink. The concept is actually very simple. Don't think so much. Don't keep thinking, why am I doing a second derivative equal to 0? It doesn't help. Treat the G like an area, like a volume. The concept doesn't change. Okay,